Welcome back to Physics 142 Online.
We're now going to look at combinations of resistors, and the two basic types, as they were with capacitors, are parallel and series combinations, so that we can learn how to simplify more complicated circuits by combining resistors in equivalent values. So if we imagine two resistors connected to each other in parallel, and then together through the wires here that aren't connected to anything, connecting those to a power supply or a battery, then we can draw a circuit diagram, of course, and then observe a couple of simple relationships that concern the voltages across the two resistors and the currents that flow through them. And the first thing that we can see, because of the parallel arrangement, is that the potential difference V1 and V2 across the two resistors have to be the same, and they have to be the same as that of a power supply connected across the two. So V, which would be the voltage of a battery connected to this arrangement, would be the same as V1 and the same as V2. And then if we have a current I leaving the battery, let's say coming out of the battery and flowing to the right through the top wire, when it reaches this junction here, part of that current can go through resistor 1 and the other part can go through resistor 2, but the sum of those two currents has to equal the total current that came out of the battery. So in other words, I1 plus I2 has to equal I. And we'll later clarify by saying that this is one of the fundamental rules for analyzing circuits. It comes simply from the conservation of charge, that the charge per unit time flowing into that node, that point at the top, has to equal the charge per unit time flowing out of that point. Charge is neither created nor destroyed. And these two observations alone allow us to draw an equivalent circuit that replaces the two resistors in series with in parallel with a single equivalent resistor. And that's very easy to do. We just write down what we observed, that the current I flowing out of the battery has to equal I1 plus I2, and then use Ohm's law to represent that current I as V over R equivalent, which is what we would have in the equivalent circuit, and then I1 is V1 over R1, I2 is V2 over R2. Remember, V1 and V2 and V are the same, right? So if we realize that, then we can divide both sides by V and get the relationship that 1 over R equivalent is 1 over R1 plus 1 over R2. And you'll notice, it's kind of interesting, that the equations for combinations of resistors are exactly the same as they were for capacitors, except that they're flipped. So this equation for capacitors was what you used for two capacitors in series, while for resistors it's the formula that's appropriate for the parallel combination. So if we consider now two resistors in series, the observations that we can make are the final currents through each of the two resistors is the same, right? Because the current that flows out of resistor 1 then is directed into resistor 2, and the charge per unit time that flows through those two guys has to be the same. There's nowhere that the charge can go. It can't increase, it can't decrease, and so I1 and I2 have to be the same, and that would be the same as the current that flowed out of the power supply, which we could just call I. Then the total voltage across the resistors R1 and R2, so if we connected these two ends to a battery, its voltage would have to be the sum of the two voltages V1 plus V2. And that, from the standpoint of an electron or just any charge moving around that circuit, it would gain energy flowing through the power supply, and that's equal to the charge times the voltage, and then it would lose energy across each of the two resistors, but in one complete circuit its energy would stay the same. And so V, in other words, is equal to V1 plus V2. This again, we'll see in a moment, can be related to the conservation of energy and is therefore a fundamental law that for circuits simply relates the voltages of two elements that are in series. So the equivalent circuit then for two resistors in series is the same. It replaces the two R1 and R2 by an equivalent resistor, and then we can find R equivalent by just starting with the sum of the two voltages, V1 plus V2 is equal to V. Once again, we'll use Ohm's law to replace each of those voltages by a current times a resistance. So the total V for the equivalent circuit is IREQ, while V1 and V2 are equal to I1R1 and I2R2 respectively. We already said that the total current flowing out of the power supply has to equal I1 and has to equal I2, so those allow us to divide both sides by I and get that the equivalent resistance is the sum of the two resistors. And again, it's just the opposite of what we found for two capacitors that are in series with one another. So these two equations look very similar, but you have to keep them straight between resistors and capacitors. Now, we're going to look at the analysis of a rather complicated circuit that's composed of more than one loop, and that's what makes the analysis a little bit challenging. For a single loop circuit, we can just combine any resistors that we have into equivalent resistors and then find the current and then find potential difference across each of the resistors, and ultimately, if we want to, we can find the power that's dissipated through each of those resistors. But to analyze a more complicated multi-loop circuit, we have to use the general principles of conservation of charge and energy. And that gives us two rules that are called Kirchoff's rules or Kirchoff's laws. The first we've already stated in a specific case where the total current flowing into any junction or any node of a circuit is equal to the total current flowing out of that junction. This is sometimes called the node rule or Kirchoff's current law. And the sum of the potential difference or voltages around any closed loop in a circuit is equal to zero. And this is a manifestation of the conservation of energy, while the first rule is a manifestation of the conservation of charge. The second rule is sometimes called the loop rule or Kirchoff's voltage law, depending on the textbook that you read. So let's show how to use those two rules to analyze circuits with resistors. These will be multi-loop circuits where we will have to write down Kirchoff's laws more than once, one for each loop present, and here we'll just show how to do this symbolically. In class, we'll work through an example that uses numerical values. So, consider a simple circuit that's got more than one loop. So you've got resistors R1 and R2 on the right-hand side, R3 on the bottom, and then two power supplies that we think of as ideal voltage sources, epsilon 1 and epsilon 2. So how do we find the current through each of the resistors, and therefore how do we find the power dissipated by each resistor? What's the strategy for doing this? And we can't simply combine all three resistors into some equivalent resistance because we've got this additional power supply. And that's what makes this problem a little bit more challenging. So what do? Here are the steps that you will use in the analysis of any multi-loop circuit. First, draw in the currents in each circuit branch, picking a direction and labeling it clearly. You just have to, you don't know for sure which direction the currents will flow, and if you find out you're wrong at the end of the problem, you will simply get a minus sign that will say, okay, here's the magnitude, but the direction you originally chose was opposite. After you label currents, then you'll label the high and low potential ends of each resistor, remembering that current flows from high to low potential. I'll illustrate this in just a minute. And then, after you've done the first two steps, then you'll be in a position to write Kirchoff's rules for at least one node and for as many loops that you need to solve for the unknown currents. So in this problem up here, we'll see in just a moment that there are three currents. There's the current that goes through resistor 3, resistor 1, and resistor 2. So we will need three equations in step 3 in order to allow us to solve for the three unknown currents. And we need to pay attention to signs as we do this. So here's our circuit again. And let's draw in, we don't know for sure which way the current's going to flow through R1, but let's just draw it downward. For R2, since the power supply is set up this way, it makes it look like it's going to generate a current flowing in that direction. And then for the power supply on the left, we'll call this I3 because if we trace it backwards, we'll see it's the current flowing through resistor 3. So let's just assume those directions and those labels for the currents, and now we can write down the label the potential across each resistor from high to low potential. So look at resistor 1. If the current is flowing downward, then the current always flows from high to low potential. So we're labeling the two ends of the resistor, not in any way indicating that it's like a power supply, but simply saying the high potential end is the top, the low potential end is the bottom. So let's do the same with resistor 2. Since the current flows through resistor 2 upward, we've assumed that direction, then the polarity will look like this. The plus end, the high potential end, will be the bottom. The low potential end will be the top. And similarly for resistor 3. Okay, we can see that the current flowing through resistor 3, I3, goes from right to left, and so the high potential end will be on the right, the low potential end on the left. I find this is not a necessary step, but it's a very helpful step to me as I solve these problems. So then, the node rule we can write down. Let's just pick the top node up here where the three arrows are either pointing into or out of that. And the node rule is simple. The current that flows out of that node, I1, is the sum of the two currents flowing into it, I2 plus I3. That should be relatively straightforward. And now let's look at the loop rule applied to the left-hand loop, the one that includes currents I3 and I1. And so that's pretty easy to write down. I'm going to go around this loop clockwise, starting with the power supply. So as I go upward across the power supply, potential is going up. And so Kirchoff's loop rule says the sum of all the potential differences has to equal 0. So epsilon 1 is a positive potential difference moving in a clockwise direction. And now I1 is flowing downward through R1. And notice we've already labeled the high and low potential ends, so the potential difference across R1 will be negative because we're going from high to low, and it's I1 times R1. So we have epsilon 1, which is positive, I1 R1, which is negative. Now what about R3? Well, the current flowing through it is I3. We've labeled high and low potential ends, so this will be minus I3 R3. And that brings us back to where we started, so that combination, epsilon 1 minus I1 R1 minus I3 R3 is equal to 0. And remember, the signs in front of each of these terms simply tells us as we go across that element, in this case in the clockwise direction, is the potential going up or down. So let's now write down the loop rule for the loop on the right hand side, and here, because the current I2 that I've defined is flowing upward, I'm going to start at the bottom of the power supply and go in the counterclockwise direction. And you'll see what we get in just a moment. The first term will be E2, that's positive. Then for R2 we get I2 R2, and that's negative. We've already indicated the high and low potential sides of that. Then we drop down through the middle branch, and that's again, we're going from high to low potential, so that's minus I1 R1. That brings us back to where we started, and so epsilon 2 minus I2 R2 minus I1 R1 is equal to 0, and we now have three equations with three unknowns. We assume in this problem that we know what the voltages epsilon 1 and epsilon 2 are. We know what the resistances are. We simply want to find the three currents. So three equations that are independent equations with three unknowns should give us enough information to solve the problem. And clearly, in order to get some practice doing this to make sure we understand it, we need to do some examples. But I hope this helps introduce the topic and that you'll be ready to work some examples in class time. I'll see you there.